What if the biggest alien signal story of the year was never a signal at all? And what if the real discovery hiding underneath that headline is even more unsettling? Before we go deeper, do this with me. Tap like if space still gives you chills. Subscribe if you want the truth behind the hype, and share this with the one friend who would call you instantly if aliens were finally found. A few minutes ago, the internet made it sound like James Webb caught a message from beyond our solar system. That is not what happened. Webb did not hear a voice. It did not catch a radio beam. It did not decode a transmission from an advanced civilization. What it found was much quieter, much harder to explain, and in some ways much more powerful. It found a possible chemical trace inside the atmosphere of a distant planet. And on Earth, that same kind of chemistry is strongly linked to life. That sentence alone is enough to make your mind race, but if we rush too fast, we miss the part that matters most. Because this is not a clean story. It is a story about hope, caution, disagreement, and one planet that has forced scientists to ask a brutal question. Are we getting close to the first real sign of life beyond Earth? Or are we being fooled by a few tiny distortions in starlight? The planet at the center of all this is called K2-18b. It sits about 120 to 124 light years away, circling a small red dwarf star in the constellation Leo. It is not Earth-like in the simple way people imagine. It is much larger than Earth, about 2.6 times wider and roughly 8.6 times more massive. That puts it in a class called sub-Neptunes, worlds that are bigger than rocky planets like ours, but smaller than giant planets like Neptune. We do not have anything quite like that in our own solar system, and that makes planets like K2-18b both exciting and frustrating. We are trying to understand a kind of world we cannot compare to anything close to home, and yet K2-18b sits in something even more interesting than a strange category. It sits in its star's habitable zone. That is the region where temperatures can allow liquid water under the right conditions. Because its star is cooler and dimmer than our sun, the habitable zone is much closer in. K2-18b races around its star in only about 33 days, but that short year does not automatically make it a furnace. Around a red dwarf close can still be comfortable. That one fact made K2-18b one of the best targets for studying a potentially habitable world in real detail. And that is where the James Webb Space Telescope enters the story. Webb is not just a camera floating in space. It is more like a machine for reading hidden patterns in light. It works especially well in infrared, which makes it powerful for studying distant worlds and faint signals. Now, when a planet passes in front of its star from our point of view, a tiny fraction of the starlight passes through that planet's atmosphere before reaching the telescope. Different gases block different colors, or wavelengths of that light. So when scientists spread the light out into a spectrum, they can look for missing pieces, tiny dents in the pattern, and use those dents to figure out which molecules may be present. Imagine trying to identify the air around a planet more than 100 light years away by studying a tiny filter of light. That is what Webb is doing. It is precise, difficult, and full of room for mistakes if the data are weak or the assumptions are off. Here is what makes it even more intense. Scientists are not looking at a giant, obvious atmospheric label that says methane here, carbon dioxide there. They are measuring tiny changes in light during a short transit window, then comparing that pattern against models of what different atmospheres should look like. Clouds can blur the picture. Instrument noise can blur the picture. The chemistry of the planet itself can blur the picture. Even the way the data are grouped and smoothed can slightly shift what seems to stand out. So every result in a case like this sits on a tightrope between astonishing precision and dangerous overconfidence. Still, Webb is the best tool we have ever had for this kind of work. And when it looked at K2-18b, it found something worth paying attention to. In 2023, Webb data showed methane and carbon dioxide in the planet's atmosphere. That was already a big deal. Those are carbon-bearing molecules, and their presence gave scientists a better picture of what kind of world they were looking at. At the same time, there seemed to be little ammonia. That combination mattered because it fit a bold idea proposed by astronomer Niku Madhusudan and his team that K2 or 18b might be what they call a Hycean world. That word sounds futuristic, but the idea behind it is simple. A Hycean world would be a planet with a thick, hydrogen-rich atmosphere, and below it, a huge liquid ocean. Not an Earth twin, something stranger, something with very different skies, very different pressure, and possibly very different forms of habitability. The low ammonia mattered because ammonia can dissolve into water. So if there really is a deep ocean below the atmosphere, that ocean could help explain why ammonia looks scarce above it. And this is what made K2-18b so attractive to researchers. Earth-sized planets are wonderful to dream about, but they are hard to study. Their atmospheres are smaller targets. Their signals are weaker. A larger world like K2-18b offers a thicker envelope of gas for Webb to read. That means it might reveal its chemistry more clearly, even if the planet itself is nothing like Earth. In a strange way, a weirder planet can be easier to study than a familiar one. That did not prove the planet had an ocean or could support life. NASA stressed that being in the habitable zone does not automatically make a planet habitable. It could still be too hot, too extreme, or more like a mini Neptune than a living world. But the picture was intriguing enough that the planet moved from interesting to intensely watched. Then came the claim that set the internet on fire. In April 2025, a Cambridge-led team reported signs of either dimethyl sulfide, called DMS, or a related molecule called dimethyl disulfide, called DMDS, in K2-18b's atmosphere using Webb's mid-infrared instrument. On Earth, DMS is strongly associated with life, especially marine microorganisms like phytoplankton. That is why so many headlines exploded into phrases like possible sign of life, strongest hint yet, or signal from beyond our solar system. But pause there. This is the moment where public excitement and scientific language start moving at two different speeds. The researchers did not say aliens were confirmed. They did not say intelligent life had been found. They did not even say life was the only possible explanation. What they said was more careful and, in some ways, even more dramatic. Based on the data they had, the best fit seemed to include molecules that on Earth are linked to biology. They also said more data were needed. They openly admitted that unknown non-biological chemistry might still explain the signal. Even in their excitement, caution was part of the story. Another detail made the claim feel even bigger. The Cambridge release said the possible amounts of DMS or DMDS could be thousands of times stronger than what we usually see in Earth's atmosphere. If that were true, then either biology or some unknown chemistry would be reshaping the atmosphere on a shocking scale. Still, once those words hit the public, the simplified version took over. A signal, life, maybe even aliens. The internet loves a shortcut, and this story had all the ingredients. A famous telescope, a strange world, a chemical link to life, and a claim big enough to make people feel history might be happening in real time. If this story has you leaning in, let me ask for a tiny favor in return. Leave a like. So more curious minds find this video. Subscribe if you want science without the smoke machine, and share it with someone who loves the moment where mystery meets evidence. Now, here is where the story gets much more interesting than the headline. Almost immediately, other scientists started pulling the claim apart. Not because they wanted it to fail, not because they were trying to kill a great discovery, but because that is what good science is supposed to do when the stakes are this high. One of the earliest skeptical reactions came from researchers who reanalyzed the same data and argued that the evidence for DMS or DMDS was not solid enough. Some said the apparent signal could be sitting right at the edge of noise. Others argued that the result depended too much on the model you chose before looking at the data. In simple words, if your answer changes a lot, depending on how you process the light, how you group the numbers, or what chemical possibilities you allow, then your detection is not yet robust. Think about a blurry photo. If one person sees a face, another sees a shadow, and a third says the image is too noisy to call it anything, the problem is not just what is in the picture is not clean enough yet. That is what happened with K2-18b. Some scientists saw a possible biological clue, others said it was a maybe sitting on top of a maybe. NPR reported that one independent researcher, Jake Taylor of Oxford, ran a simple reanalysis and found the data consistent with a flat line, meaning the supposed wiggle that hinted at a special molecule may not stand out clearly enough from the noise. Other experts said the evidence seemed too dependent on the fine details of interpretation. Laura Kreidberg, a leading expert on exoplanet atmospheres, pointed out that for a strong detection, you want the signal to survive even when the assumptions change. That was not clearly happening here, and that is a key lesson in this whole story. The danger is not only false hope, it is also false certainty. If we want to say we have seen a biosignature, a true sign of life, the evidence has to be able to survive attack from every angle. This is where the word sigma enters the conversation. You may have heard people throw it around in articles and videos as if it settles everything. It does not. Sigma is a way of describing confidence. A 3 sigma result can be exciting, but it is not the same as a final answer. For truly historic discoveries, especially something as massive as life beyond Earth, scientists usually want something closer to 5 sigma. That is a far tougher bar, much less likely to be a statistical fluke. The DMS claim was around the lower, more tentative level, enough to publish, enough to debate, nowhere near enough to close the case. And the deeper researchers looked, the more complicated it got. Some follow-up analyses said other molecules could fit the data too. Some found that small technical choices changed the outcome more than they should have. Imagine chopping the same set of numbers into slightly different bins and finding that only some versions produce the exciting result. That is a warning sign. It suggests the signal is fragile. Later reporting described a NASA-led collaborative study that combined new Webb observations with older data and painted a much more careful picture. It supported the idea that K2-18b has a water-rich atmosphere along with methane and carbon dioxide, but it did not find conclusive evidence for DMS. In other words, the planet remained fascinating, but the biggest claim remained unresolved. That matters. Because if the water-rich atmosphere is real, if the methane and carbon dioxide are really there, and if this world does have conditions that resemble the Hycean idea, then K2-18b is still one of the most important exoplanets we know. It is still a world on the frontier of one of humanity's oldest questions. It just is not a solved mystery, and honestly, that may be the best part. Real discovery is usually messy. It arrives as doubt, debate, rechecking, disagreement, and more data. There is another huge misunderstanding built into this story, and we need to clear it up before going any further. The word signal has been used in a way that confuses almost everyone. What Webb detected, or may have detected, is not a message. It is not a radio call. It is not an intentional beacon aimed at Earth. It is a chemical fingerprint buried in starlight. That may sound less dramatic, but in reality it is astonishing. A planet passes in front of its star. A thin layer of atmosphere filters the star's light. Webb catches that altered light. Scientists analyze the missing wavelengths and try to identify the gases involved. That is the signal. It is a pattern in light, not a transmission from a civilization. Why is that distinction important? Because when people hear signal from beyond our solar system, they imagine intelligence and purpose. But nothing in this Webb story points to an intentional message. In fact, a completely separate search looked for that kind of thing. In 2026, researchers used two powerful radio telescope arrays, the Very Large Array in New Mexico and Meerkat in South Africa, to search the K2-18 system for narrowband radio technosignatures. That is the kind of signal you might expect from technology. A focused radio transmission that does not usually arise from natural cosmic sources. The team watched the system across a huge frequency range, from hundreds of megahertz up to nearly 10 gigahertz, and tracked it across roughly the full orbital period of K2-18b. They processed millions of signals and filtered out ordinary interference from Earth and other false leads. The filtering shows how hard this work is. A real signal from K2-18b should drift in frequency over time because the planet is moving. It should also behave differently when the planet moves behind its star and come from the direction of the system, not from local interference. Researchers used those checks to eliminate candidate after candidate. What did they find? Nothing that matched a technological origin. That does not prove there is no intelligent life there. It does not prove the planet is dead. It does not even prove no civilization exists. It only tells us that this search, with this method, found no radio transmission consistent with a technological source in that system. So the clean, honest version is this. No alien radio message has been detected from K2-18b. No confirmed evidence of technology has been found. The real scientific mystery is chemical, not conversational. Life, if it exists there, is not speaking to us, at least not in any way we can hear. The question is whether it may be quietly changing the chemistry of its world. And that question is so difficult that one molecule alone may never be enough. This is one of the hardest parts of the search for life beyond Earth. Very few molecules are perfect smoking guns. Volcanoes, radiation, impacts, rock atmosphere reactions, ultraviolet light, and deep atmospheric chemistry can all produce things that look alive. On the other hand, real life might exist and still leave almost no clear trace that we can see from that distance. So astrobiology has been moving toward a more careful mindset. Instead of betting everything on one miracle molecule, scientists increasingly look for combinations of gases, environmental context, planetary structure, temperature, pressure, stellar activity, and repeated observations that all point in the same direction. It is like building a case in court. One clue may be interesting. 10 clues that agree with each other are harder to ignore. That is why K2-18b remains so important even though the loudest claim is still disputed. It is not just about DMS. It is about whether this strange world is the first place where we can seriously test a new idea of habitability. For decades, people searching for life mostly dreamed of finding another Earth, same size, same kind of atmosphere, same kind of orbit. But Earth-sized planets are extremely hard to study in detail. Their signals are small, their atmospheres are thin, their stars often drown them out. K2-18b is different. Bigger planet, thicker atmosphere, easier to probe. If worlds like this can host oceans or chemistry friendly to life, then the galaxy may have far more possible homes for life. That possibility is thrilling, but it also creates a trap. The more we want a world to be special, the more careful we have to be. Quick pulse check. If you like stories where wonder survives but hype gets cut down to size, hit subscribe, drop a like, and share this video with one person who wants the truth before the rumor. History gives us a warning here. In 2020, scientists announced phosphine in the clouds of Venus. and the public immediately heard the same whisper, possible life. Phosphine is a strange gas. On Earth, it is strongly tied to human industry and certain biological settings. For a moment, Venus stopped being a dead hellscape in the public imagination and became a maybe world, a place where microbes float. Then came reanalysis, alternative explanations, questions about the data, debate over processing choices. The story cooled. Go back even further to 1996, and you find another famous case. Researchers studying a Martian meteorite announced fossil-like signs of life. The world paid attention. Even the President of the United States spoke about it. But confidence dropped as scientists showed alternative origins. Notice the pattern. Big claim, huge excitement, hard questions, slower truth. If life is really out there, we want solid evidence. We want to find it in a way that survives every test. That is why the disagreement over K2-18b is not a failure of science. It is science doing exactly what it should do. And honestly, that may be the most powerful part of this entire story. Human beings built a telescope so sensitive that it can read the chemistry of a planet more than 100 light years away. Then one team found a tantalizing hint, then other teams challenged it, then more teams rechecked it, then new observations were added. The planet stayed on the table, not as proven, not as dismissed, but as an open case. That is not confusion. That is discipline. And discipline matters more than excitement when the prize is the most important discovery in modern science. Imagine the day we finally do confirm life beyond Earth. Not maybe, not suggestive, not headline ready, confirmed. When that day comes, you will want to know that the claims survived skepticism, alternative models, and better data. The standard is brutal because the consequence is enormous. K2-18b may one day pass that standard. It may not. But even now it is teaching scientists how to ask the question better. Future telescopes will matter here. Webb is incredible. But it was not built only for hunting life. It is doing many jobs. Better limits and more refined spectroscopy will be needed. Missions like the Habitable Worlds Observatory are being planned with the search for biosignatures as a central goal. Those future tools could help settle arguments like this. But there is something beautiful about the timing we are living in. We are early enough that the mystery is still alive, but late enough that the question is no longer pure fantasy. We are no longer asking whether it is possible to study the atmosphere of a distant world. We are doing it. We are arguing over the details because we finally have details to argue about. That is a historic shift. For most of human history, life beyond Earth was philosophy. Now it lives in spectra, error bars, and models. I think it is more romantic, because it means the universe is moving from imagination into evidence. Real wonder begins there. Now, there is one more tension inside the K2-18b story. Suppose DMS is eventually confirmed. Would that mean life has been found? Not automatically. That is the uncomfortable truth. Even a stronger detection would trigger a battle over abiotic production. Recent modeling suggests sulfur-based molecules might be produced abiotically in hydrogen-rich atmospheres. The exact answer may depend on what K2-18b really is. If it has a thin atmosphere over an ocean, biology remains likely. If it has a deeper atmosphere with unknown chemistry, non-living processes might explain it. The finish line is context. What is the atmosphere made of? How deep is it? What role does the star play? The final answer may take years. The internet wants discovery at the speed of a thumbnail, but the universe does not care about our attention span. A distant planet will reveal itself on its own timetable. That is part of what makes K2-18b so gripping. It sits at the edge of what we can know, just clear enough to tempt us and just blurry enough to fight over. There is a deeper reason this story landed so hard. It is about loneliness. We wonder if life happened once or everywhere. Are we rare? A planet like K2-18b turns that abstract question into something physical. It gives it a location and a star. It lets us say, maybe there, maybe that world. That makes the mystery feel personal. If the universe can make life twice, then it may make life everywhere. The night sky becomes a map of possibilities. But if we are going to touch that truth, we have to earn it. We cannot let a seductive headline do the work. We cannot confuse a possible biosignature with a message. Doubt is the tool that keeps discovery honest. The real headline is that humanity has become precise enough to seriously debate whether a distant planet carries a hint of life. And we are disciplined enough to refuse the answer until the evidence is strong enough. That is a much better story. Someday, one of these worlds is going to stop being a maybe. One spectrum will survive every challenge and pattern. When that happens, the discovery will not feel like science fiction anymore. It will feel like recognition. If you want more space stories told with honesty, subscribe now, tap like, and share it with someone who looks up and wonders. Until then, K2-18b remains a pressure point where hope presses against skepticism and data meets imagination. A place where a few missing colors and a beam of starlight can shake the human picture of life in the universe. No voice has called us, no machine has greeted us, But something on that planet is forcing us to pay attention. Maybe that is how the universe first changes us, not with a shout. With a whisper so faint, it takes a great telescope to hear. If that whisper turns out to be life, we're standing near the edge of the biggest discovery our species has ever made. And if it turns out not to be life, it still means we are finally asking the question with real tools. Either way, this is a rehearsal for the future. A future where the line between maybe and proven will matter more than ever. Our descendants may look back at K218b and say, that was where the universe first started answering back. Not with words, but with chemistry, with light, with a mystery strong enough to pull a civilization closer to the truth.